life and building properties. So according to the United States fire statistics, there are about 6,500 fires per year, like costing about $400 million annually. And mass timber buildings under construction are largely unprotected as they are not yet equipped with fire protection systems. However, limited research has been conducted to demonstrate the impact of passive fire protection on a CLT building under construction, which pose a need of tools for risk assessment for this topic. Therefore, it is necessary to develop a numerical modeling solution for the early phases of a CLT construction project, which can be achieved using 4D building information models together with fire dynamics simulator. Particularly, 4D beams are 3D beam plus time, and FDS is a fire dynamics simulator tool that allows for information exchange with beam software.
That's me.
To facilitate a better understanding of fire behavior within a mass timber building under construction, this study aims to propose a beam-based simulation framework integrates with FDS. So the first step of the framework is to develop architectural 4D beams that meets at least the level of detail 300 of the 3D beam models in different construction stages. The 4D beams, once completed, are exported as IFC files for data interoperation with a target FDS program, namely Paradigm, for contact fire simulation with specific material definitions and modeling parameters. And during the simulation process, Paradigm writes post-processing simulation outputs, both as a 3D animation and a 2D time history plots for fire dynamics over time in different construction stages. There are 3 tasks for developing the proposed simulation framework. The first task is to validate the practicality of using the FDS tool together with beam software for fire dynamics simulation in a building, which was illustrated in our previous work. And the second task detailed in this paper is to use an FDS software to simulate the fundamental fire behavior of CLT panels and benchmark the simulation against the experimental data. The purpose of this study is to test the FDS numerical configuration and investigate the modeling parameters for future use towards the final task of developing the proposed simulation framework. So in this paper, the first step of the modeling approach is to develop a one-to-one FDS numerical scenario benchmarks with a small-scale compartment fire test conducted by Goskar et al. And this figure illustrates the numerical scenario developed in Paradigm with specific internal dimensions. The fuel load is provided through a calcium pore, and the compartment walls are covered in 2 layers of 12 millimeters fire shield boards that is designed as non-combustible in the fire. And for the combustible parts, that is CLT panels, are attached on the 2 lateral sides and the top of the compartment with a specific thickness sequence, and the related thermal properties for the CLT panels are listed below. The compartment walls include 1 ceiling, 2 lateral walls, and a back wall to investigate the effect of exposed CLT area on fire propagation and magnitude. We tested 8 experimental configurations with varying exposed CLT area. And the table summarizes the FDS numerical configuration matrix with different CLT surfaces exposed to fire. During the simulation, Paradigm writes post-processing simulation outputs, including the heat release rate, flow velocities, and temperature profiles. Those outputs are obtained through the measurement devices defined in the FDS numerical models. About the modeling outputs, the comparisons shown in those figures are different heat release rate from the experimental data compared with those predicted by our FDS model. Data is including the heat release rate contributed from the CLT, from the calcium, and the total heat release rate in the compartment. Particularly, The HR total is a summation of the heat release rate from the CLT and the kerosene. And the HR model is a measured total heat release rate during the test. HR model was used to determine if there were heat release rate losses within the compartment during the experiments by comparing HR model to HR total. And a satisfying match of the comparison means that the numerical model has a good prediction of the heat release rate with varied exposed CLT area. The numerical models also will predict the flow velocities obtained in the experimental fire test with a corresponding natural plane height, as well as the velocity trend. As shown in the figure, the flow velocity increases as the exposed area increases. This is due to the mass flow exchange driven by burning CLT panels. Therefore, all CLT surfaces exposed to fire would increase the flow velocities. And the evaluation of the temperature profiles indicates a thermal gradient with higher temperatures on the surface of the CLT panels exposed to fire. It can be observed from the figure that the temperature of the CLT increases with increasing depths into the CLT from the external surface to the fire-exposed surface. The data shown also indicates that at a depth of 14.5 centimeters away from the external surface, the thermal gradient levels off and the temperature slightly decreases while the CLT panels start to char. In addition, the numerical simulations can also provide additional information that cannot be obtained through an experiment. So the main advantages of numerical experiments is being more resource efficient compared to traditional experimental tests. A large-scale compartment fire test is usually costly and time-consuming. Therefore, a numerical model enables users to collect time-dependent information about fire dynamics at any location. Moreover, the numerical simulations can provide additional insights into the fire dynamics in the compartment through the 3D animations that can supplement the observations on fire dynamics from the test. So here is an example of the 3D smoke wheel for fire dynamics for the configuration of exposed ceiling in our FDS test. It shows that the CLT panels are burned away over time. So in a short summary, this study provides a modeling solution that uses paradigm to simulate and benchmark the fire behavior in CLT structures regarding heat release rate, flow velocities, and temperature profiles in a numerical compartment model. And the validation of numerical results in this paper confirms the practicality of modeling the fire's fundamental fire behavior using the FDS numerical models. So in our future work, the FDS numerical configuration and the modeling parameters will be implemented in the next step of this study to simulate and assess fires in CLT buildings and construction. In the end, thanks for the US Department of Agriculture funded our project research. And thank you for listening my presentation. Any question or suggestion for us would be greatly appreciated. Thank you so much.
Thank you, Chi, for the presentation. Any questions from the audience? Yeah, please raise your hand.